Okay, so today we'll continue studying groups with property T, and we'll start by talking about yet another operator, so-called discrete Laplace operator, which will relate to other operators we've seen, and also to other invariants. And again, this is the operator that we can consider on graphs, or so on real functions on graphs, or in more general situations with for functions with values in Hilbert space. But we'll start with the setting of a graph. Actually, it might be a finite or infinite graph. Let us say that it's finite. Then this discrete Laplace operator delta for the function f. So this is a function on the vertices with, say, real values. At the vertex x is defined as the identity f of x minus the sum of the values of the function f on the neighboring vertices. Okay, vertices which are connected to x by an edge, and we normalize, we divide by the degree of the vertex x, the number of edges adjacent to the vertex x. Okay, so if you remember the definition of the Markov operator, this Laplace operator is just the identity minus this is exactly the definition of the Markov operator we've seen in the case of graphs. Why is it called discrete Laplace operator? If you consider a grid, so well, this definition works as well for infinite graphs. Okay, the only assumption is that the number of edges at each vertex is finite. Okay, so if you consider the integers on the real line, and you consider this operator, if you then and you take a restriction of the function defined on R to this integer point, and then instead of considering the difference between neighboring vertices to be 1, you decided to be epsilon, and if you consider this operator and you divide by epsilon square, if epsilon tends to 0, you will find the second derivative. Okay, so this is just one way of arguing that this operator could be called discrete Laplace operator. Okay, there are other reasons to think about this as analog of the Laplace operator. Okay, which is defined with the second order derivatives. Okay, so this is self-adjoint operator if you consider a suitable L2 space on X. Okay, it has to be L2 with the weights, which are degrees of the vertices. So then it's a self-adjoint non-negative operator, and so its eigenvalues are real and non-negative. There is always 0, okay, because constant functions are in the kernel of this operator. If the graph is connected, it's a simple eigenvalue. Okay, but if we call the remaining eigenvalues by lambda 1, lambda 2, and so on, you get finitely many eigenvalues. Well, the number counted with multiplicities is the number of vertices in the graph. Okay, and this operator, for this operator, we'll pay special attention to lambda 1, to the first, to the second, or say first non-trivial eigenvalue. Okay, so once again, this is strictly positive if and only if the graph X is connected. Okay, but now we'll relate it to the isoperimetric constant, and we'll say that being large, lambda 1 being large, means that graphs are highly connected, that they have large isoperimetric constant. So now we'll try to relate this lambda 1 of the graph with the isoperimetric constant. So you cannot deduce one from another. However, the asymptotic behavior when the size of X is large is the same. Namely, either both of them tend to 0, or both of them stay bounded away from 0. So the equivalent definition of sequence of expanders would be that lambda 1 stays bounded away from 0. So the proposition let Xn be a sequence of finite graphs of degree k, so degree is the same, such that the size of these graphs tends to infinity. Okay? And then the following are equivalent. So the first condition is there exists a constant c such that h, the isoperimetric constant, stays bounded away. It's bounded below by this c.
It's unconnected or not? Maybe disconnected.
I think the way I'll formulate, I don't need to suppose that they are connected. Okay, so let me finish, and then we'll see. So, and the second condition is that there exists a constant, which might be different, such that lambda 1 of this graph is bounded below by c prime. Okay, and your question was about assumption of being connected. So if the graph is not connected, isometric constant is 0 and lambda 1 is 0. Okay, so I think we don't have to say that they are connected. However, of course, it's interesting only for graphs which are connected. Okay. Maybe it's easier to get some kind of intuition concerning H, because it talks about geometry of the graphs. However, if you're interested in really knowing the values, it seems that it's much easier to actually compute lambda 1. So for many families of graphs, one has very sharp estimates concerning lambda 1, and one knows very little about the isoperimetric constant, except from the estimates which are true for all graphs. So if you have, if you know lambda 1, it gives you upper and lower bounds on h, and vice versa. Okay, but they not even asymptotically they do not converge to the same number. Okay, very well. So this is I think that's it. If you talk about infinite graphs, it wouldn't be. It is not true anymore that 0 necessarily belongs to the spectrum of this operator acting on L2. Actually, from the theorem we know from the characterization of amenability concerning the random walk operator, immediately you would get the characterization of amenability coming from the fact whether 0 is in L2 spectrum of this operator. Okay, so now the amenability means that 0 is in the spectrum. If not, then you have 0 is not in the spectrum. You have so-called spectral. Then you can talk about the bottom of the L2 spectrum. Okay, very well. So now we would like to talk about proving property T for groups which are not necessarily lattices in Lie groups, and in particular we would like to obtain the proof which would not use the classification of the unitary dual for Lie groups. Okay, so the condition that we will discuss now is the following one. So we consider a group generated by finite set. Okay, so S is finite, and I think as very often in this class, we'll assume that S is a symmetric set. Okay, so to this pair gamma S, we'll associate a finite graph which we'll call SL. So this is a finite graph. Okay, and this graph is defined as follows. So the vertices of L are generators. Okay, and we'll put an edge. We'll put an edge between two generators, S and S prime, if they differ by another generator. Okay, so this S inverse S prime is again in the set of generators. Okay, so this is a finite set, and then from this graph, in some cases, one can actually prove that the group has property T. So the theorem that I proved is that if, and here just to avoid this discussion, maybe let us suppose that L is connected, and the first 0 eigenvalue, if lambda 1, yeah, it's connected graph, so it's strictly positive of L, is strictly greater than 1/2, then gamma has Kazhdan's property T. Okay, so there are few comments that that we would like to make. So first of all, lambda, well, 1/2 is certainly optimal. Remark, 1/2 is optimal. So in order to see this, let us consider the simplest group which doesn't have property T. So what is the simplest group? Z. Okay. So let us take gamma integers. Okay. So what are the generators that we would like to take? Well, if we take plus minus 1, this graph L of S, so it would have two vertices, minus 1, 1, but the difference between 1 and minus 1 is 2, yeah? So the graph is not connected. So actually this condition, graph being connected, is not restrictive. It's easy to see that you can always enlarge the set of generators so that the graph becomes connected. Yeah, it's actually enough to take for instance, plus minus 2. Yeah, it's enough to take the square of any set of generators, and it becomes connected. Yeah, in this case, if we add minus 2 and 2, so the difference between minus 2 and minus 1 is 1. The difference between 1 and 2 is 1, so we put an edge. And the difference between minus 1 and 1 is 2, but now 2 is a generator, okay? So we should connect these two vertices, so the graph is connected. Okay, and now you have to compute lambda 1. So by the way, it's computing lambda 1, this is computer can do for any finite graph. Okay, so this is something, this is the information for finite graphs which are not too large, you can always get. It's actually, if it has 4 vertices, it's really easy to compute, right? It's very easy to compute. You can compute all because so there is an eigenvalue 0 corresponding to the constant function. Okay, then when you take the function 1 minus 1, 1 minus 1, then you get eigenvalue 2, and the remaining one will be 1.5 and 1/2. Okay, so the smallest one is 1/2. Okay. And here we put strictly greater than 1/2. Okay, so we cannot put any number which is less than 1/2. Okay, there is also yet another thing that. Here we really have some number associated, yeah, to this pair, to gamma S, okay, lambda 1, and being strictly greater than 1/2 implies property T, and actually the difference between lambda 1 and 1/2 can give information in some sense how much property T we have, namely for all the applications that we mentioned here, for instance, expander graphs. Yeah, we mentioned this Margulis result, how to getting expanders property T. So actually, this lambda 1 will give an estimate, explicit estimate on the expansions constant for these graphs. So here, maybe let us mention here the definition of so-called Kazhdan constants. So for a group gamma generated by a finite set S, okay, we define this constant, okay. So for a group gamma with a finite set of generators as so how could we measure this? How far away we are from the trivial representation? So we would consider all unitary representations without invariant vectors. Okay, and once we have such a representation, we would like to see if there are almost invariant vectors. Okay, so we will take the infimum over all vectors if we consider a Hilbert space and this H, so this P is a unitary representation in a Hilbert space H, so we take the infimum over all vectors, and now we will consider the difference pi of S V minus V, and for instance we'll try to see if there is at least one vector, so we'll take the maximum over all set of generators. If this is large, well, compared to the size of the vector V. Okay, so here we consider non-trivial vectors. Okay, so this being strictly positive, okay, means that there is no unitary representation without invariant vectors, which would have almost invariant vectors, right? I think we have right infimum maximum. Okay, so this constant being strictly positive is equivalent to having property T. Here the choice of taking maximum is arbitrary. Okay, instead of taking maximum, we could take, for instance, the sum. There are several possibilities to define it. Okay, for a as far as property T is concerned, them being positive, it's equivalent to property T. However, for different applications you are interested in, it might be interesting actually to consider the variance of this constant. Okay, then it's not really when you vary property. So maybe let me write it also. It's possible to have like different constant when you. So maybe let me call it blue, and here you could take, for instance, the sum instead of the maximum. And for some applications, it's actually quite tricky to deal with this constants when you also want to get information when you vary set of generators. Okay, then there are very interesting applications. So also please think what is the most suitable definition of this constant if you want to get information about expansion of graphs. Okay, if you want to get an estimate from this constant of the isoperimetric constant. Okay, so also so a second remark would be that from the difference between lambda 1 and 1/2, one gets estimates, non-trivial estimates on Kazhdan's constants. Yeah, estimates on Kazhdan constants. Okay, so this is, yes, it should be one of these constants, for instance, say maximum, it's called Kazhdan constant. Okay. Actually, it was at some point an open problem how to define Kazhdan constants independently on set of generators. Okay, so we're going back to the discussion we had at the beginning of this these lectures. So the question was whether, for instance, if you take the infimum over all set of generators, you could still obtain something strictly positive and non-trivial invariant. Okay, so there will be constants again that if it's strictly positive, it would be equivalent to the fact that gamma has property T. So this question was asked by Lubotsky, and counterexample was obtained in a joint work with Glander. Okay, there is a group with property T, and there is a sequence of set of generators such that so if you take even like this, even maximum, and you can do it with the even just set of generators of size 2, the isoperimetric, this Kazhdan constant will tend to 0. Okay, so it really depends on the set, or essentially on the set of generators. Okay, so maybe now let us see examples of groups for which you can give this elementary proof of property T by looking just at this one finite graph. Okay, so we'll start with the example, which is actually the lattice in p-adic groups. So property T was known for this group using exactly representation theory of the ambient group, but one can give this this elementary proof. So we'll be talking about lattices in SL3QP, and we'll be interested in the lattices which, if you know the theory of Tits buildings, associated Tits buildings act simply transitively on the vertices of these buildings. Then for such groups you can find a set of finite set of generators such that this finite graph L of gamma S will be incidence graph of finite projective planes over Fp. Okay. What does it mean? Incidence graph, it means that the vertices of this graph will be the points and lines in this finite projective plane. Okay, and we'll put an edge between, the edges will be only between points and lines. Okay, if X lies on this line L.
Points multiplying, huh?
Points. This is a point, this is a line, and the point X belongs to the line L. Then we put an edge. Okay, let me draw a picture corresponding to the simplest case when P is equal to 2. Okay, so then we have 7 points and 7 lines. Okay, so let us put. So these are points. This would be lines. This would also 7. Okay, and the lines and the edges in this graph will be the following ones. Right, plus the following. This one. This one. This one. This one. This one. And this one. Okay, so this is the graph. Okay, and for this graph you can compute. It's a finite graph. You can compute lambda 1, and if it's strictly greater than 1/2, then you know that the group has property T. Actually, this it might look complicated, yeah, because it has 14 vertices. So you might think that you're not able to do it like immediately without a computer, but actually it's very easy. We'll do it. We'll compute it, and maybe we'll even compute it for OOPs. Okay. We'll do it for OOPs. So the reason is that this graph is very much symmetric. Yeah, it has many symmetries, and the computation of eigenvalues is very easy. Okay, so let us do it not only for this graph but for all OOPs, and actually I think. We'll manage to compute all eigenvalues, okay? Not only lambda 1. Okay, so let us. So in order to compute all the eigenvalues, we will draw this graph in a slightly different manner. Okay, maybe it will look less beautiful. I'm sorry. Okay, but it will be more helpful. So the way we'll do it, we choose, or maybe here, so that you see the difference. So we choose one point in this finite projective plane. Okay, let us call it x, x naught. So this is connected to all lines that contain x. Okay, so here let us put all lines. So these are lines L which contain x. Okay, and we have the edges between these lines and this vertex. Okay, there are p plus 1 lines which contain x for any vertex. Okay, then on this level, let us put all the vertices which are different from this vertex x. Okay, and finally, on the last level, let us put the vertices corresponding to lines which do not contain the vertex x. Okay, in this way we put all vertices. We have all vertices in this graph. Okay, and the edges are only between vertices which lie on the neighboring levels. Okay, so the lines which are these lines L, okay, they cannot be connected with lines. Okay, the edges are only between points. So here we have some edges, okay, between lines which contain x and vertices which are different from x. And the vertices on these lines, there are lines which do not contain x, so they're not connected with x. They cannot be connected to other lines. They can be only connected to these vertices which are different from x. Okay, so the other edges in these graphs are these ones. Okay, why is it useful to draw this graph in this way? Because now, if you look at the automorphism of this finite projective plane, which fixes one vertex, okay, it acts transitively on lines which contain x, okay. So it acts transitively on each of these levels. What does it imply? That if we look at the equation, this discrete Laplace delta f lambda f, okay, f is a function on the vertices, lambda so we're looking at the eigenfunction corresponding to the eigenvalue lambda, okay. It follows that in such a space, so eigenspace corresponding to lambda, there is a non-zero eigenfunction which is constant on each of these levels. Okay? Actually, we can suppose that the value of this function is 1 on the vertex x. Okay? Why? Because the function, if you take any function, eigenfunction non-zero, it is non-zero of some of these vertices in this graph. So we can actually suppose that it's a vertex corresponding to some point x. It could be to a line, but by duality we can suppose that the value of this there is an eigenfunction corresponding to lambda which is equal to 1 on the vertex corresponding to x. Okay, then if you look at this automorphism, which fixes the vertex x, okay, under this any automorphism of the graph, if you apply it to the function f, you obtain a new to eigenfunction, you obtain a new eigenfunction. Okay, so it means that there is an eigenfunction which is actually invariant under this automorphism group. Okay, so we can suppose, so there is in the subspace there is a function which is 1 at x, which is equal to a on this level, which is equal to b on this level, and which is equal to c on this level.
We just average.
Yes, you just average, and in this way you get a function which is constant. Okay, first you average on this level, so you obtain this 1, then it's b, then you average, you obtain is equal to b here, and then you average, you obtain which is equal to c on the last. Okay, so at the end, this problem which looked so difficult to find eigenfunctions, we are left with equations we'll write for separately for a point at each level. Okay, so we obtain 4 equations. So for instance, if we write this equation at here at the vertex, okay, so it means that so what is delta f? Its identity, it will be 1 minus the mean over this neighboring vertices. So what is the mean? It's a. Okay, so minus a is equal to lambda times 1. Okay, this is the equation. Okay, if you write it now here, so it will be identity, which is a minus the mean over neighboring vertices. Now, there is one vertex x, okay, the value here is 1, and there are p neighbors, the graph is of degree p plus 1, okay, so there are p vertices where the value is b, so it's p times b over p plus 1, and this is equal to lambda times a. Okay, and similarly, you write equation at the point b, where the value is b, and where the value is c. Okay, and okay, this is we consider it to be advanced class, so maybe I won't solve this equation, but I'll write you already the answer. Yeah, so or maybe you will tell me the answer from this four equations. Okay, we get that what are the eigenvalues? So there will be just 4. Yeah, 4 are known. So there is 0 corresponding to constant functions. Okay, there is 2. Okay, if you take the function equal 1, minus 1, 1, and minus 1. Right, yeah, if you take the function equal 1, minus 1, 1, minus 1, you will get 2. Okay, so this was easy. There are 2 remaining eigenvalues. By the way, these are they are with the multiplicity 1. Okay, so the remaining 2 will have large multiplicity, and the remaining one is 1 minus and 1 plus something. And the something is square root of p over p plus 1. Okay, actually the graph is so-called bipartite. Yeah, so the it's you know that the spectrum is symmetric around 1. Okay, so if you have 0, you have 2. If you have 1 minus something, you have 1 plus the same number. Okay, so these are in this way. So as you can see, in many cases it might be actually very easy to compute all eigenvalues of this operator, even for infinite families of graphs. Okay, when there is a lot of symmetry, the computation might be very simple. And there are also methods just to try to get an estimate on lambda 1, and that's what we are interested in. Anyway, so lambda 1 in this case, let us write, so lambda 1 is equal to 1 minus square root of p over p plus 1. Okay, so actually already for p equal to 2, this is square root of 2 divided by 3. So this is slightly less than 1/2, right? It's square root is 1 point. Yeah, sorry?
Yeah, the denominator is always more than 2 numerator.
Of course, yeah. Right. So this is greater to 1/2, even already in the smallest, and it gives maybe the simplest proof of property T for an infinite group. So actually this this can be defined for groups which are given by a presentation, and now we'll try to discuss the case of groups given by presentations, and how one could possibly prove property T for them. And there will be like 2 parts proving property T, and then in order to have as a non-trivial result how to prove that actually this group is infinite, and these are 2 separate questions. So we'll be considering groups given by presentations. So there is a set of generators, say S1, Sm, and relators R1, Rk. Okay, so relators are freely irreducible words one writes using these generators and the inverses. So the group you obtain in this way is a quotient of a free group of rank m by the smallest normal subgroup which contains these words. And actually it appears that many groups do admit finite presentations. Okay, so any group generated by a finite set of generators can be defined in this way. If you admit infinitely many relators, you can write just O relations in the non-trivial relations in your group. But we'll be interested in the ones which are which can be given by this finite presentation, like for instance the group Z square. Okay, so there are of course infinitely many relations, but it admits a finite presentations with the generators which we call A and B, which correspond to standard vectors 0, 1 and 1, 0, the presentations would be actually the just one relation, which is the commutator. Okay, so which is A, B, A inverse, B inverse, and all other relations are the consequence of this one. Okay, are in the smallest normal subgroup, which contains this word. Okay, now we'll be interested in the following, now in the notion of then on Van Kampen diagrams. So each of these relators, we will to each of these relators we will associate polygon, yeah, in the plane, such that its edges will be labeled by generators. And if you read the word on the boundary, you obtain this relator, and we're using also orientation for the edges. Okay, so the polygon corresponding to this relator will be the following one. Okay, so this is the labeling of edges, and the orientation is as follows. So that if we read now the word in this with this orientation, if the orientation of the edges is according to its clockwise, then we take a generator as it is. If it's not, if this opposite, we'll take the inverse of the generator. Okay, so here it's A, B, but here is A inverse, and here is B inverse. Okay, and with this we are allowed to consider several copies of the same corresponding to the same relator. And now we can attach this disk, we can glue them along common edges which are labeled by the same letters, and in such a way that the orientations do match. Okay, so for instance, if we take yet another copy, A, B, B, A. For instance, we can glue these two edges. Okay, and in this way, we obtain the disk, which is labeled here. It's A. Here its boundary is labeled by A. Now B. Here it's A. Here is A, and here is B with this orientation. So now if you read the word which is you have on the boundary, you obtain here A, B, A inverse, and finally B inverse. So of course this word is trivial in the group Z square. Actually, what we just described is the way of finding all words which represent trivial element in this group, and this is general. So for any group given by a finite presentation, okay, you can obtain this Dehn or Van Kampen diagrams. So the condition is, as we said, that you glue the edges which are labeled by the same letter and orientations should match. And also when you do this gluing, when you attach yet other cells, you should always obtain planar, so it should be always homomorphic to a disk. Okay, it's not so that the boundary would be a circle. Okay, this is the only condition. Then the words that you read on the boundary correspond to trivial elements in the group, and any trivial element in the group can be obtained as the boundary of such a diagram. Okay, so this will call this D diagram, and its boundary will be denoted by DD. So in this case, we'll so is this word, and in general, in the group gamma, the boundary its identity in the group, and any word which represents identity can be obtained as the boundary of such a diagram. Okay, it's a simple observation, but really very deep, very profound. In general, if you have a word representing a trivial element, there might be several diagrams which have this word as the boundary. Okay, so given the word, trivial word, we can represent it as the boundary of this finite diagram. However, they might not be unicity. There might be several different diagrams which would have the same boundary. Okay, so for a given boundary among all diagrams, we'll consider the minimal one, minimal with respect to a number of cells, and as we say, cells correspond to relators. Okay, and in this, and we'll be interested in groups such that
there is multi. Please.
Pardon?
Repeat, please.
Right. So we'll consider for a given word representing trivial element, we will consider the diagram which has minimal number of cells among all diagrams which have this given word as a boundary. Okay? Very well, and we'll be interested in the following groups, such that there exists a positive constant C, such that the size of the boundary is at least C times the size of D. So these are minimal. This then on Van Kampen diagrams. Okay, this is for every and this inequality, you have already a lot of intuition, because this is exactly the one which we have, this isoperimetric inequality, which we have for graphs which were non-amenable. Okay, this is exactly this one, that the boundary is at least c times the size. Okay, that amenability corresponds to situation that the boundary divided by d would tend to 0 for some sequence of subsets, like call it Fellner sequence. Okay, and such groups, the family of groups for which this is true, are called hyperbolic groups.
So here we measure the number of edges, right?
Yes, yes, exactly. So this is the number of edges, or it is the length of the word of this trivial word. Okay.
Each D minimum.
So this is a minimal. We call it minimal diagram. So that here we defined it with respect to number of cells. Okay. So for the fixed boundary, this is the one which has the smallest number of cells. Okay.
So this constant is for all words?
Yes. So there is a constant such this is true for every d. Yeah.
This is the property of the group, not the representation.
And one can prove that this is a property of a group. Okay. So this is one possible definitions. Actually, the one which is very useful when you want to prove this property for some families of groups, and I will indicate why. Okay, for us it will be useful when we want to prove property T for groups given by finite presentations. When we want to property T, and also we would like to say that they are infinite. Okay? Okay, so this condition among the groups being finitely presented, this is equivalent that to being a fundamental group of a closed manifold. Okay, and it's actually also interesting to restrict attention to this class, because there are many conjectures which are open exactly for fundamental groups of closed manifolds, for finitely presented groups. And indeed, here we would like to present some constructions of finitely presented groups, for instance, using random methods, okay, similar to the ones we've seen in the case of graphs. So we'll talk about random groups. So there are, as in the case of graphs, there are several models, ways of constructing groups using probabilistic methods. There is, for instance, a model due to Gromov. Here I will describe a different model, and I thought about this model exactly to be able to use this criterion concerning lambda 1 greater than 1/2 to obtain new groups with property T. So the model I considered is the following one. So maybe let me write once again the presentation with with generators we call S1, Sm, and with relators we'll call R1, Rk. But in the model I consider, the relations will be of length 3. Okay, so this is actually a small presentation is not unique for a given group, and it's a small exercise that any finitely presented group admits presentation with relators of length 3. Okay, that you can in some sense triangulate any presentation to obtain. So this is for any relator, its length is 3. Okay. So in this way we in this model we consider all finitely presented groups. Okay. So and here we'll be considering for a given M, which is arbitrary. What will be interesting is the number of relators we'll put, and we'll measure it as follows. We'll introduce a parameter called density. So it's number between 0 and 1. This is the density. Okay. So this is the parameter which we'll fix. That we'll fix. And then M will vary, and the number of relators we consider will depend on this density. So the number of relators, okay, this k, it will be 2m minus 1 to the power 3 times d. Okay, so maybe what is the meaning of this number? Okay, so if we consider here 2m minus 1 to the power 3, it's roughly the number of all relations or words of length 3 you can write using m generators and the inverses. Okay, if you consider okay, so this is the number, it's rough number of all relators you consider. So you can get, so if you put d, it's like the proportion in logarithmic scale of the number of considering the number of relators you put in this presentation. Okay, so now we will call it gamma m d. All presentations. So there'll be presentations with m generators and density D. Okay, so somehow, yeah, this is important. That we obtained some properties with groups. Maybe actually, let me.
So excuse me. So this is the number of these presentations, or what?
This is the set.
The set.
This is a finite set of all the presentations, which look as follows. We have M generators and relations. Relators we write are the words of length 3, okay, and the number we put here, it's this number, okay. It's a finite for every M. This is a finite number, and we'll be interested in properties of groups given by such presentations when n tends to infinity. Okay, this is the setting. Okay, this is analog of these models we've seen for random graphs. Okay, the number of vertices was tending to infinity, and for instance, some model we were choosing k permutations on the set of these vertices. Okay. Right, and here again, it's like it's important that we're not talking about. So we will be counting presentations and not the groups. Okay, we are counting presentations.
Maybe some of them are
Right. So kind of all the comments we said in the case of graphs do apply in this setting. Okay, so this is also the way of avoiding this kind of difficult questions about when two presentations defined groups which are isomorphic or not. Okay, but the point is that one way of looking of this construction is that you want to find groups with, for instance, if you want to find the groups with several interesting properties, you can prove that these properties asymptotically hold with probability 1 in this model, so also the intersection, okay, is not non-trivial. Okay, and the results that one can prove exactly in this model. So the first theorem is that concerning property T. So if density is strictly greater than 1/3, then if you count the number of and here maybe so there are maybe I'll choose here maybe the letter like P, just that we're really talking about presentations, okay, not the group that we count. So the number of presentations in the set PMD, okay, it's as we said, it's a finite set, such that this presentation defines a group with property T, okay, and if we divide it by the number of O presentations, and if we take the limit when m tends to infinity, is 1. Okay, so for large M, almost all these presentations will define a group which has property T. And 1/3 here is sharp. So if D is less than 1/3, then if you count the presentation here, which defines a group with property T, okay, and you divide by the number of all such presentations, then the limit is 0. Okay, so it's
maybe we should say something about finiteness of the group, because if they are finite, it's not interesting.
right. So then it looks like that this is more interesting, yeah, because it doesn't have T, then it's in particular it's infinite. But oh yeah, sure, okay.
And
yeah, of course we'll comment on it in a second. Okay, so the way to so this, by the way, this is that it doesn't have property T. It's a simple observation, but how do you prove that it has property T? So actually, for this given presentation, you can construct this graph L of S so for this triangular presentations, you can construct this graph L of S, where the vertices correspond to generators, and the inverses. Okay, and then you put an edge. If so the condition was that we would take a generator, and we put an edge between one generator and another if the product of this generator and the inverse of the other is again in the set of generators. Okay, so it exactly corresponds to the relation of length 3. Okay, so that's why I thought about this model with relators of length 3, because this is exactly the graph you obtain when you want to apply this criterion lambda 1 greater than 1/2. Okay, and actually in this you can put prove the version of this theorem where the only edges you consider here are the ones corresponding to these relators. Okay, there might be other relations in your group which are consequences, and would be also of length 3, but actually in the definition of this graph you can consider only the ones coming from the presentation. Okay, so you know exactly what is the graph given the presentation, what is the graph L you consider. Okay, so it might be in principle a different graph L prime, but the point is that we avoid all these difficult problems concerning the groups. Okay, here we don't know if the group you ask being finite, we don't even know if it's trivial or not. Okay, it might be trivial. It might be a trivial group. However, it might be the case that some generators actually are in the group. The sum of these letters in the group, they are the same. Okay, the group might also collapse or might be trivial, but still we can consider this graph L prime such that the vertices are labeled by these letters S1, Sm, and by their inverses. And we put an edge when we put the edges which will correspond to these relators. Okay, in the way we describe. Okay, so it's a slightly different version of the theorem we just seen, but in this way, it's one. If you know presentation, it's very easy to know what is this graph L prime of S. And now you can prove that these graphs you obtain, they correspond to some model of random graphs. Okay, we've seen in one of the models for random graphs, we've seen this result showing that isomorphic constant is large. Just from the information of the isomorphic constant, you cannot deduce that lambda 1 is as large that is larger than 1/2. One needs more refined information about the lambda 1 for random graphs, but actually, as far as lambda 1 is concerned, there are very precise estimates for random graphs in different models. There are much more facts known than just about that isomorphic constant. Somehow, if you look at the history subject of this random graphs, this theorem we've seen is just the beginning, but then the subject really concerned the information about lambda 1. Okay, it's we didn't talk about these results, but actually it's much easier to work with lambda 1. So one can prove that in particular lambda 1 is greater than 1/2, and actually in this situation it tends to 1. So you also obtain good estimates concerning Kazan constants for these families of groups. Anyway, so this is the way you prove property T, and the fact that you don't have property T, it's an observation. Okay, so now what about proving that these are infinite? So in this model,
are there similar theorems, for example, just for the number of graphs which define, let's say, finite group or trivial group? There should be some, no? If I just want to know if it defines a
okay.
say,
Okay, maybe we'll see if what I write now will answer your question. Okay, so in order to see this distinction between finite, actually trivial, and infinite, the threshold will be 1/2. Okay, so if density is strictly less than 1/2, then the number of presentations in this model, triangular model, such that defines an infinite hyperbolic group and actually I could here put more hyperbolic, also torsion free. Okay, so it's like stronger way of saying it's infinite. There are even no elements, non-trivial elements of finite order. Okay, and if we divide it here by the number of all presentations, so when m tends to infinity, it's equal to 1. Okay, so almost surely then you get infinite group, and if d is strictly greater than 1/2, then if you consider the number of presentations which defines the trivial group, okay, then this limit is equal to 1. Okay, so this is what you were asking for. It's nothing like it's trivial. Everything collapses. Okay, and here, so from this, so if you are between 1/3 and 1/2, so with that with the corresponding number of relators, you almost surely get infinite torsion groups which have property T. And the way to prove it is really it's a work with this then Van Kampen diagrams. So the presentation one works with is really the one given by these relators of length 3. Okay, so this is important that we don't do any work with the presentations. They are really the ones. This is really the presentation which is suitable for proving this result. And the point is that actually in order to prove this inequality, it's enough to do it for finitely many diagrams. Okay, so this is related to like planar geometry. Okay, this is related to planar geometry. So in order to prove this expansion property, it's enough to do it for finitely many. Right? If you do it, if you prove this inequality for finitely many diagrams, but with the suitable constants, it implies that this is true for all. You have this expansion for all diagrams. Maybe just to like give you kind of indication how you what is get the feel what kind of.
What happens if d is equal to 1?
Right. So yeah. So yeah. So of course it's for many reasons it's very interesting to understand what happens for 1/2, and and the point is that in order like to consider this case 1/2, you can also refine this model. You can say more precisely how do you grow with the number of relators. Okay, so you can
generators. The number
of
relators will be fixed.
no. Number of, so we go to infinity with the number of generators, but the number of relators grows with number of relators. Okay, and here I said that this is how it grows. Okay, now when we want to say something about this critical, then we can actually consider the situation when this will that it will grow, not exactly when we put here one half, but for instance, but faster than any of these numbers. Well, here we put any d, which is strictly less than 1/2. Okay, so we can approach this 1/2, and there are some. Also, you can prove that it's. You can prove this kind of results, and this is actually, I think, very interesting to understand the situation. What happens when we approach this 1/2? So we know that if we cross 1/2, then everything collapses. Okay, but this is very interesting to understand very well this model. So you can do slightly better. You can also d can tend to 1/2, but there are only partial results concerning this situation. But this is really it's really interesting. Okay, this this moment just before it collapses and also it might be, so here we have this kind of distinction. It's like torsion free, and here it's trivial, but maybe also there will be this way to catch finite groups. Okay, this is very interesting models, and I describe here kind of really just the simplest situation. Okay, when concerning the number of relators, but when one talks about this limit cases, one can refine the description of this function with concerning the number of relators we are allowed to put. Okay. Very well. Okay, so right, and one can also, so here we get in this interval we get this infinite torsion-free hyperbolic groups with property T, but one can also put more conditions on this group. Okay, so here is an example where by intersecting this sets of presentations which almost surely define groups with some properties, you end up with new examples of groups. Okay, very well. So there are. This is somehow just
For d smaller than 1/3, what happens there? Maybe an inability.
You mean equal to 1/3?
Yeah, smaller than 1/3.
Strictly. So how do you? Okay, how?
It's no mistake that it should be no without property T. Yes.
I think so. I wrote it here 0.
Oh, excuse me.
So okay.
And maybe there is an inability.
So yeah, boundary
results
for...
before.
Okay, so the way I proved this, so the way I prove this result, so this is small, yeah. So you have still we are infinite, we are torsion-free hyperbolic, okay. So it's non-amenable. But the way I prove it is by showing that actually this group have homomorphism on Z, have infinite abelianization. Okay, and it's easy to see from the...
is named random group, yes?
Yes.
Yes. Where random?
So here is that you can interpret this theorem as follows. So we consider generators S1, Sm, okay, and we put at random that many relators of length 3, and almost surely, asymptotically, when m tends to infinity, most of these choices with the probability going to 1 will define to a group with a property. Okay, it's here like property T, or might be or different properties. Okay, that's why we call it random groups by analogy with random graphs. Okay, this is exactly the same setting. Yes, right. So these are, yes, and this is, so we didn't use here the geometric definition, but this definition using this Van Kampen diagrams, because this is really the ones that is very suitable for this work. This is the one that you use to prove these results. Okay. There are also many other models of random groups. For instance, Gromov had a model which was based on graphs with the large graph, with the graphs which do not have small cycles, and also using probabilistic considerations. You can build the graphs in you can build interesting groups in this model. Actually, interesting. At some point, Gromov thought that he might get in this way groups for which you cannot prove Novikov conjecture. It was like the interest in all this. Construction is trying to produce new groups which might answer some very interesting questions in group theory or in topology. We're talking here about finitely, in this model, in finitely presented groups, but actually it appears to be really trivial that groups given by his construction satisfy Novikov conjecture, but maybe one could answer other problems in group theory by this kind of constructions.